Hi, I'm Travis and I'm an application engineer at Maxim Integrated. When designing portable systems to have both an internal battery and a connector to apply power from a wall adapter or USB port, it's pretty common to use single-use, non-rechargeable batteries because they're cheap and widely available. However, there needs to be a way to switch between the two power sources that is efficient, safe, and seamless. Circuits that automatically switch between two power sources are called diode ORing circuits, even if they don't include any diodes, as they're named after the first component used to accomplish this function, diodes. I'll talk about a few industry standard ways to do diode ORing, and then show you the tiniest possible diode ORing circuit using the MAX40200 ideal diode. The classic approach to switching between power sources is to use Schottky diodes, as they are simple two-terminal devices and have a low forward voltage to reduce power loss. When the outputs of two Schottky diodes are tied together, the one with the higher voltage applied conducts, which reverse biases the other diode. However, using Schottky diodes poses two problems. First, their forward voltage, although lower than other diodes, still contributes to large power losses, which is lost as heat. For example, if a Schottky diode has a 300 millivolt forward voltage and is supplying a 3.3 volt rail, there is a constant 10% power loss in the diode alone. When operating from a battery in a tiny device, power loss and heat should be minimized at all costs. Second, when a Schottky diode is reverse biased, a leakage current forms. Most non-rechargeable battery manufacturers warn against such unsafe trickle charging. If a Schottky diode is reverse biased and starts to charge a non-rechargeable battery, safety becomes a critical concern. One way to overcome the power loss from a Schottky diode's forward voltage is to use a MOSFET in place of the diode, as the low drain-to-source resistance reduces the power loss through the current path. However, one drawback to using a MOSFET instead of a Schottky diode is the requirement for additional control circuitry to turn the MOSFET on and off. Several semiconductor manufacturers now offer a single-chip solution with MOSFET and controller integrated together. The controller circuit typically looks something like this, with both inputs feeding into one diode ORing switch and a few external resistors for setting an input threshold and a current limit. When it comes to portable systems that operate from battery or USB input, one solution that addresses both the disadvantage of Schottky diode parasitics and the increased size of diode ORing controllers is an ideal diode IC like the MAX40200. For applications that require tiny footprint, low forward voltage, low reverse leakage, and low cost, it is a highly competitive option. In a 0.7mm by 0.7mm package, it offers a forward voltage drop of 85 millivolts at 1 amp, which is significantly less than most Schottky diodes. Searching several electronics distributor websites, I can find small Schottky diodes rated down to 220 millivolts at 1 amp. I did find one with the forward voltage rating of 120 millivolts at 10 amps and excellent reverse current rating, but that one is 50 times the size. When searching other diode ORing IC solutions, the MAX40200's tiny size makes using two of these devices more efficient than using other single-chip solution with larger area. There are also many products out there designed to be powered externally, but have an internal battery backup in case the external power supply fails. For products like this, where the battery is fully charged and perhaps not in use for years, having low reverse current when the battery is inactive is critical. Plus, when the battery becomes active in keeping the system alive when power is lost, a low forward voltage drop extends the battery backup runtime. For today's demo, I'll be using the MAX40200 evaluation kit. It has two MAX40200 ICs with their outputs connected together to protect two different input sources. The evaluation kit has a layout that's spread out so it's easy to work with, but in an actual design I could really shrink down the size of that circuit. I have two AA batteries generating 3 volts connected to one input, an external 5 volt supply connected to the other input, and an 8 ohm resistive load attached to the output. Here are some multimeters monitoring the two input voltages, the output voltage, and the resistive load monitoring current. I'll superimpose these meters onto a circuit diagram so we can look at what's going on. When the 5 volt supply is powered off, you can see that the battery voltage is discharging into the load. The input from the batteries is 2.709 volts, and the output of the diode ORing circuit is 2.668 volts, which shows roughly a 41 millivolt drop across the diode ORing circuit. With the 5-volt supply enabled, the measured input voltage is 4.991 volts, and the output voltage is 4.948 volts, which shows roughly a 43 millivolt drop across the diode ORing circuit. The load current jumps up because I'm applying a different voltage, but there would usually be an LDO or step-down regulator to keep the voltage across the load constant. I get several customer questions asking whether the second ideal diode, the one in the path of the external power supply, is really necessary, as it will reverse bias the one connected to the battery. While this may seem like a good way to save cost or space, it really depends on external components and the layout of your system. If there are any parasitics or energy storage elements in your circuit that could cause reverse current into the power supply, that could cause damage. Now, I always lean towards safety and keep that second MAX40200, because safety never takes a vacation. That's all for today. In under 6 minutes, I showed you a few different trends in the evolution of diode ORing portable circuits and how to create the tiniest and most efficient diode ORing circuit using the MAX40200 ideal diode. For more information, check out the product page or the design solutions linked in the video description. That's all for now. I'll see you next time.